Hi students, today we are going to look at how to find out the force on a current carrying conductor, and this is one of the derivation based on the mechanical effect of current. So whenever a current carrying conductor is placed in a magnetic field, it will experience a mechanical force. So we are going to measure that force using a simple derivations and simple diagrams. Okay, let's look at the diagram here. Here along z-axis, magnetic field is acting. Along x, OX dash axis, a conductor is placed whose length is L. This is y-axis. So this is y-z plane. Here in this conductor, these are the free electrons which are drifted along this direction, and this is the direction of flow of current. So if any current carrying conductor is placed in a magnetic field, the electrons present inside the conductor will experience a magnetic Lorentz force. So this total number of free electrons will make the whole conductor to move along y-axis. So this is the direction of force. So here we are following the Fleming's left-hand rule. It is also called as a motor rule. So here the forefinger denotes the field. Also here is z-axis. The middle finger denotes the flow of current. Here it denotes the x-axis. The thumb denotes the direction of the mechanical force experienced by the conductor. It is also nothing but the y-axis. So this is compared with this diagram. Okay. Now, using these two diagrams, we are going to do the derivations. First, let's look on to the theory. Here, small l be the length of the conductor, capital A be the area of cross-section of the conductor, capital B be the magnetic field which is acting along z-axis, and I be the current flow in the conductor or wire. Here V suffix d be the drift velocity of the free electrons inside the conductor. Small n be the number of free electrons per unit volume. I into L vector is called as a current element vector or current element. Capital N be the total number of free electrons inside the conductor. Small e be the charge of one electron. F vector, small f vector be the magnetic Lorentz force experienced by one free electron. Capital F vector is the total magnetic Lorentz force on all the free electrons which is acting along y-axis. Okay, now we will proceed on to the explanation part. Now, we know that the relation between current and drift velocity is I is equal to N capital A E V suffix D. I equal to Neuwied. Okay. So if this equation I equal to Neuwied, in that equation let us multiply both sides by L. So the equation becomes IL vector is equal to minus NAEL V suffix D, which is taken as equation 1. Here the negative sign indicates the direction of current is opposite to the direction of flow of electrons. Here the free electrons are moving in the presence of magnetic field. So the magnetic Lorentz force on one free electron is F vector, that is small f vector, is equal to minus E of V suffix D vector cross B vector, which is taken as equation 2. This is nothing but the equation compared with the magnetic Lorentz force equation. F vector is equal to Q of V cross B. Here the negative sign indicates the charge of electron is negative. If the total number of free electron, capital N, is equal to small NaL, then the total Lorentz force on all the free electrons will be capital F vector is equal to capital N into small f vector. So capital N is nothing but NaL, and small f vector is nothing but minus E of V suffix d cross B vector. So F vector is equal to minus NaEL V suffix d cross B vector, which is taken as equation 3. Here the minus NaEL V suffix d is nothing but the current element IL vector is equal to this. So let us substitute the value here. So here capital F vector is equal to IL vector cross B vector, or it can also be written as F is equal to BIL sin theta, because according to the vector product of two vectors we get this formula. So this is the mechanical force experienced by a current carrying conductor when it is placed in a magnetic field. Okay, here some points have to be considered here. The first point is, if the wire or conductor is placed along the direction of magnetic field, then theta will be equal to 0. So the force will be equal to 0 because sine 0 degree is equal to 0. So the diagram 3 here, the conductor is placed along z-axis, that is the direction of magnetic field is along z-axis. So theta equal to 0, so the force equal to 0. The second point to be considered, if the wire is placed perpendicular to the direction of magnetic field, that is theta equal to 90 degree, then F is equal to BIL, since sine 90 degree is equal to 1 in the diagram 4. So here, so this is nothing but the diagram which has been shown on your first page. So here the conductor is placed along x-axis. It is perpendicular to the direction of magnetic field B, which is along z-axis. So theta equal to 90 degree. So the magnetic Lorentz force F vector will be acting along y-axis, that is, which is equal to BIL. Okay. The third point to be considered is the direction of force on the current carrying conductor is always given by the Fleming's left-hand rule. It is also called as motor rule because Fleming's left-hand rule is applied in motor. Okay. So I think you must have understood the concept clearly. Thank you, students.